Hello everyone. This is Dhanlakshmi, Assistant Professor from Triple Department of R&D Engineering College. In this session, I would like to discuss about power Mosfet. So in the previous video, we were discussing about the power BJT, bipolar junction transistor. Now I would like to discuss about power Mosfet. So we all be knowing about Mosfet. Again, it's a power Mosfet as discussed earlier. Power, when the term power comes, it should be capable of handling high rating, high power rating. So here we can see the symbol of power MOSFET. Here again, it is having three terminals: drain, source, and gate. And we can also say that MOSFET has a IG FET, that is insulated gate field effect transistor, where here the gate is insulated by a metal oxide layer. So that is the concept of MOSFET, and that's why we say it is an insulated gate, IG FET, insulated gate field effect transistor. So that IG insulated gate, it has been insulated with the metal oxide layer. So here we can see some of the features of MOSFET. As we discussed, the three terminals, drain, source, and gate. It's a voltage control device, whereas BJT is a current control device, where the base current, where the base current is going to control the flow, right? Where it is going to control the device, whereas here the voltage, VGS, the gate source voltage will be the controlling parameter. So that's why we say that this is a voltage controlled device, and it's a unipolar device. Like BJT is not bipolar here, so it is unipolar. So where we have two the types of MOSFETs here, N channel and P channel, and here the gate circuit impedance is very high, and here the control signal required to turn on the MOSFET is lesser than required signal for the BJT. Here we don't have the second breakdown problem. So, and it has positive temperature coefficient, so the thermal runaway problem will not happen here. And when we take the circuit here, you can see that the circuit, in essence, not the circuit, the exact structure of N channel power MOSFET is shown here. So where you can see that it is a N layer, from N layer, the source terminal has been taken. So here you can see that the source is formed from this N channel, and there is a N layer, and this drain is formed from this N layer, and you can see that in between we have a P substrate, and this P substrate from where we have to take the gate, but here the gate is an insulated one. So here you can see that there is a layer, there is a metal oxide layer, which is our silicon dioxide layer. Metal oxide layer is our silicon dioxide layer. Over that layer, the gate has been formed here. Gate terminal has been fetched. So here we can the thing is, always we know that the source, the power flow will the current flow will be from drain to source. So here we can see that the voltage source is connected here. The voltage source is connected between drain and source. So from drain to source, the supply voltage is given, but even then it is not conducting here. You can see that it is not conducting, because still now you just for time being just assume that we have not given any gate source voltage. So if the gate source voltage is not given, there will not be any conduction. And here you can see that once the gate source voltage, once the gate is triggered, that is once the gate source voltage is connected, here you can see that under the at the gate terminal, the positive polarity is connected, and from the where the source it is negative is connected to the source. So what happens here is it will induce an electric field here due to the excitation at the gate terminal. Here we can see that due to the excitation at the gate terminal, here we can see that there is an electric field induced under the gate terminal. Right, and because of this induced electric field, there will be an electrons will be penetrating on the P layer, right? Because these positive polarity charges will attract negative charges, and that's why we are getting all the electrons accumulating at this portion. All the electrons are accumulating at this portion, and it seems to be like it is forming like a channel. It is forming like a channel between this N layer, and this N layer. So you can see that there is a channel formed between drain and source. So from the drain, the current will be flowing through this channel to the source, so like this. So this is how it is working. So once the gate source voltage is given, an electric field is induced under that gate terminal, and because of that, in the P substrate you can see. So here we have our P substrate. In that P substrate, the electrons are accumulating at this point, and it forms like a channel between our drain and source. It is connecting our drain and source. It acts like a channel, N channel. So therefore, it is connecting our drain and source. So therefore, now the current will be flowing from drain to source. So this is how this MOSFET is working. Right? Okay, let me erase all these things. Therefore, this is how this MOSFET is working. So, when we take a MOSFET, it is not that only one single cell will be there. There are a number of cells in series, right? There will be a number of cells embedded in a common substratum. So, therefore, here you can see that. So, here we can see that this is the structure, right? This is the symbol of both. We'll go to the structure later. So here we can see that the symbol of P channel as well as for the N channel. So this is our P channel MOSFET and this is our N channel MOSFET, and this is the entire structure of a MOSFET. That is in a single silicon wafer. In a single silicon wafer, many MOSFET cells, series of cells will be there. So that's what's shown here. This is actually one cell. This is actually one cell, and here as we discussed in the earliest and the previous slide, that is for a normal MOSFET, right? As we know that there is a difference between a signal level device and the power device. Here it is a power MOSFET, which means that it should have a drift region, because as we discussed in the earlier session, that is a drift region makes the differentiation between a normal device and the power device. Only because of the drift region, the device possesses a capability of handling high voltage, high current, and high power. So therefore, if a device has to be a power device, it should obviously have the drift region, where the drift region is our this N minus region. Okay. So here you can see that this is our drift region, which is our N minus region, lightly doped N layer. This drift region is the only difference that makes the device to become a power device. So here you can see that this is one part of our MOSFET. That is one cell actually. This is actually the another cell of MOSFET. So the working, as we said already, when the gate source voltage is, when the gate is triggered, what will happen? The electrons in the P layer, right? That the electrons in the P substrate will be accumulating here. That forms an N channel between this source, between this N channel source and there is N layer of the source and the drain layer of this N layer of the drain. That is, it is connecting between the drain and source. And now thus you can see that from the drain, here is our drain terminal. So you can see that from the drain, the current is flowing to the source through this channel. So this is how the MOSFET is working. The characteristics, right? So we can go to the characteristics of MOSFET. Here we can the same thing, it is shown in this picture where you can understand better. So where this N plus layer is our drain layer, this is our drip layer, this is P, and this is our source layer. Their gate is formed in isolatedly, that is insulated gate has been formed here. And you can see here, this is the characteristics of the MOSFET, where when you take the characteristics of MOSFET as we discussed in by BJT, here also we have three regions. One is our cutoff region. So you can see that here we have the cutoff region. So this region is our cutoff region. Whenever you want to operate the MOSFET in off state, and whenever you operate the MOSFET as a switch, and when you want to turn off that switch, that is an off state, you should operate in cutoff region. So this region, the cutoff region is the off state, and here we can see that the saturation region is the on state, right? So as you shift between the cutoff region and the saturation region, it will be working as a switch, as we discussed already, right? So saturation region is our on state and cutoff region is our off state. So whenever you want to operate as a switch, it should be operated between cutoff region and the saturation region. Thank you.